So Smith chart is invented by P.H. Smith in 1939, and we know that the Smith chart is a transformation from impedance Z in the complex plane to gamma in the complex plane as well. And Smith chart is also a transformation of complex admittance, that is the Y, to complex gamma. So how to convert the Z, so this is the so-called Z chart. So it's a transformation for Z to gamma. How to convert it into Y chart? Well, to convert it into Y chart, you simply rotate it by 190 degrees. And this will become the so-called Y chart. Y chart, admittance chart. And we will talk about that later. Okay, so here we would like to discuss some basics about the Smith chart. So we know that the any value of the load, any value of the impedance can be drawn on the Smith chart. It's a one-to-one relationship, and even though the Smith chart looks like, well, all those circles and curves are labeled with Z, with R and X value. But in fact, it's a representation of the reflection coefficient gamma because of this transformation relationship. So assuming that the impedance we are looking at is R plus JX, then using this relationship, we can find out the expression for the reflection coefficient gamma. That is R plus JX minus 1 divided by R plus JX plus 1. Then we can separate them in terms of real number and complex number. So the real part of the denominator is R minus 1, the imaginary part is JX. And for the denominator, the real part is R plus 1, and the imaginary part is JX as well. And how about the magnitude? The magnitude of gamma can be found in terms of R and X like this. And you should be able to show that because R and X are real numbers. Now, they can be positive or negative real numbers, but no matter what, as long as they are real numbers, this expression is equal or smaller than 1. It must be equal to or smaller than 1. So the reflection coefficient magnitude is smaller or equal to 1. The minimum for the reflection coefficient is 0. The maximum for the magnitude of reflection coefficient is 1. This is valid for all passive components. So that is valid for passive components. So any transmission line component that does not require a power supply can be referred as passive component. Can you name a few active microwave circuit components? 你可以举几个例子吗？主动元件。电晶体，对啊 ，transistor 啊，放大器啊，要吃电的都算主动啊，不吃电的都算被动啊。所以 filter 呢 ，filter 一般讲非被动的吧，天线呢，被动的，一般来讲也被动的啦，当然现在你有所谓的主动电线，那当然是加了一些主动的电晶体元件等等的，OK， 所以主被动在所谓的主动就是说，它的讯号可能会越来越大，但是正常的微波元件，你的讯号都是越走越小，因为元件本身会有耗损OK， 好。Alright, so in general, for passive components, the reflection coefficient for all passive components will lie within the unit circle. So the boundary of the Smith chart is referred as the unit circle, unit magnitude, unit circle. And we know, I have mentioned that the transformation between impedance and the reflection coefficient is one-to-one relationship. So all the reflection coefficient of passive components can be found within the unit circle. So we know the real part of the reflection coefficient can be subtracted as this. So this is the real part, and this is the imaginary part. So actually, this is your x coordinate. That's your coordinate on the real axis. This is the coordinate of your imaginary axis. So this is the y coordinate. So the first one is x coordinate, the second one is y coordinate. y 轴跟 x 轴的坐标从伽马的那个表示是得来的吧？你把伽马的式子写出来，然后把它分成实部跟虚部。所以实部就在 complex plane 的那个实数 x 轴上面找到嘛，这边从 y 轴上面找到。Okay. So let's now discuss some different cases. If the load, if the termination is purely real, purely resistive, then the x part equals to 0, and you have some R value for your resistive termination. Then the reflection coefficient becomes a simple expression of R minus 1 divided by R plus 1, and the imaginary part is 0. So then on the Smith chart or on the complex plane, the gamma is found only on the x-axis. If gamma is a number greater than 1, then you can find it on the right-hand side of the complex plane. Then on the left-hand side of the complex plane, you find the reflection coefficient smaller than 1. So the range is from 0 to 1. And to the right, the range is from 1 to infinity. So if the resistance, the input resistance is greater than 1, then it should be found on the right-hand side of the Smith chart. So the significance is on the right-hand side, the resistance is greater than Z sub 0. It's greater than your characteristic impedance. On the left-hand side, the resistance is smaller than the characteristic impedance. Next, so we just discussed case A. Next, we will discuss case B. For pure reactive load, that is R equal to 0 and X equals to any value. Let's check. All right. So for the second case, if Z is purely imaginary, that is R equal to 0, then the expression for gamma, for the reflection coefficient, is reduced to this. And you see, the magnitude is 1 for all cases. If you have a purely imaginary termination. Why? Because a purely reactive load does not absorb any energy. So the magnitude of the reflection coefficient must equal to 1. And you will end up with complete standing wave pattern. The SWR ratio shall equals to infinity. So if you found the reflection coefficient on the unit circle, then the SWR is infinity. Is infinity. So the magnitude of the reflection coefficient is 1 for all pure reactive load. The only difference is the phase, which can be found by dividing the imaginary part with the real part and taking the arctangent of that. So that will be 2x divided by x to the square minus 1. If x is equal to 0, then what kind of law do you have? If x equal to 0, you have a short, right? So the angle of gamma is what? 0. If x is an infinite number, you have an open termination. So if x goes to infinity, you will have what? What is the angle? If x goes to infinity, oh, you will get 0. Okay, it's x to the square. So you have 0 here, and the arctangent of 0 is 180 degrees. You will find the gamma on the other side, on the left-hand side. And if x equals to 1, you will find the phase equals to 90 degrees. And if x equals to minus 1, you will find the gamma at the bottom of the circle. All right, so I already mentioned that pure imaginary value of z are found on the unit circle because they do not take energy. So the reflection coefficient magnitude is 1 for all time, for all cases. Next case is you have a complex number for your input impedance z, but the real part is a constant. So we can draw the so-called constant R circle. Why? Because if you substitute the R with a fixed number, then the expression for this will equal to can be found as this relationship, and it's a formula. It's the formula for a circle. So if you supply different value of x with a fixed value of r, you will draw a circle on the complex plane, on the gamma plane. So this small circle corresponds to gamma equal to 3. This circle, which goes through the origin, is the circle for r equal to 1, which means the resistance part is the same as the characteristic impedance of the transmission line. So this circle, R equal to 1 circle, is particularly important in the use of Smith chart. So you should pay attention about this circle. And if R is a number smaller than 1, for example, here is the circle for R equal to 1/3, R equal to 0.333. Okay? It's a circle that is greater than R equal to 1. And it's intersect with the real axis on the left-hand side of the origin. All right? And the outmost circle is the circle for R equal to 0. So as you can see, as the R number equals from 0 to infinity, well, this is the range for R. R is a resistance, is a number, is a pure real positive number. Resistance is a number greater than 0, while the reactance X can be infinity to minus infinity, right? But R is not a negative number for passive components. If you have an active component, then the R value can be a number smaller than 0, which means the signal will get larger and larger as it propagates, which is not the case for passive components. All right? So, as you can see, you have many circles found on the complex plane. do they share the same origin for the circles? No, right? The center of the circle are moving from left to right. For r equal to 0 circle, the center of the circle is found at the origin over here. When r value increases, it moves to the right. And here is the position for r value much larger than 1, which is as it approaches to infinity, the center of the circle will reach this point that is 1. That is 1. As you can see here, the center the coordinate of the center of the circles are divided by r plus 1. So if r is a very large number, this will approaches to 1. And the radius is 1 over r plus 1. So for large r value, the circle will become smaller and smaller. Let's see. Okay, so the next case is fix x for equal reactance. So z is a complex number. R is any positive value that you can choose from, but x is a fixed number. So for the case, for x equals to a constant, the relationship looks like this. You see, it can still be expressed as a circle, as a line of a circular line, like this. So this is the radius of the circle, and 1 over x are the center of the circle. So for different x value, the corresponding circle centers are found at here. So what is the implication of this? Well, this means the centers of different value of x, which can be real 1 and which can be positive 1 and negative 1, will be this red line. The union of all different x value will form this straight line, which has the real part is 1, the imaginary part is anything. And the circles of different fixed x value will only show a small fraction in the unit circle. So they will not appear as a complete circle in the Smith chart. So you only see these curves that goes up, and these curves goes down. So for the ones goes up, it represents positive x value. So they are referred as inductive reactance. For x smaller than 0, they are referred as capacitive reactance. The constant x circle will goes down, and they will not form a complete circle within the Smith chart. And the center of those circles are moving up and down outside of the unit circle. So that are the basic property you can have. And in this course, we will be only concerning the Smith chart for passive components, which will all be found within the unit circle. But if R can be negative number, then you can also draw the Smith chart for active components, which may located outside of the unit circle. 这是比较好玩的地方了，都用整个对称起来了 好了，但这个主动元件它不是我们这一个学期要教的东西了哈。好，那我们剩5分钟，我想 example 我们就下礼拜再讲了哈。那个这一张那张单子的背面有几个简单的问题哈，我们就一起看看吧哈。所以 A 的那个 A 的反射系数是多少哈？这个你记得下，我看我觉得来不及了哈，下次带来好不好？下次带来我们再一起来看一下哈，看一下 A、B、C 点。事实上就是用这个 chart， 你可以找出它所对应的反射系数啊什么的那些的哈。